Hello, this is our first look for Year 13 Further Maths at mean and variance for work from Chapter 8. And we're looking at exercise 8a. We're looking at combining the distributions of two different random variables. And I suppose it's the main difference of what we've seen in the past. So a little reminder, I suppose, we might be useful to just remind ourselves of this. We've seen these two formulas before, that if we know what E of x is, and we know what the var of x is, very often we are told the mean and the variance. So this is quite common to be given these. We are often asked then for alternative variances and means, and so we use these formulas. You can see that E of ax plus c. Notice it's like what we describe as a linear combination. So it's something a number times by x plus c. There's no squared things going on there. But if we get this, we can say that E of ax plus c is a E of x. That's sort of what you'd expect to get, I suppose. And the variance isn't quite. I suppose this comes from the fact that the standard deviation has to be squared to get the variance. So in that case, it's not unreasonable to think, hang on a bit, the variance of ax plus c is a squared times the variance. Notice again, the c doesn't matter. If I add a number onto a random variable, all the values change, and therefore they're not any more spread out. So the c is gone when it comes to here. These are two formulas then we're meant to know. Here's a little question. It says E of x is 2.4, okay, and the variance of x is 1.5. Find E of 2x plus 5. Okay, so that's very similar to this up here. I could find E of x very quickly, E of 2x plus 5, sorry. And it will simply be two lots of E of x, two lots of the x. What was x? It was 2.4. So it's two lots of 2.4 plus 5. And that's almost exactly what you'd expect it to be. 4.8, 9.8. There you go. Now the variance is the slightly weird one. The variance of 2x plus 5. The 5 doesn't matter. Who cares? But what does matter is the fact that I have to take out that 2 and I square it. So it's 4 times by 1.5, and that equals 6, or 6.0, I suppose, if we draw to 1 dp. Yeah, I wrote it as 6.0. So those two answers are important, that we understand the process of how I got them. Now, a couple of things just to note. Sometimes we want to combine two distributions, x and y. Now, they have to be independent in order for me to do so, but what I've written here is they can still be drawn from the same population. So although I've called it x and y, it could be x and x, I suppose. Now, because it's a potential for a bit of confusion here, we use this notation. We say x1 and x2. That means we've basically got two different observations from the distribution. So if I'm looking at the, I don't know, the heights of people, I've got one height, I've got another height. Whereas 2x means basically I've only got one height, but I've doubled the result. So just be aware of the two subtle differences in notation that we have to be able to use. And let's now have a look at an example of where this kind of thing comes up. So I've got an example. A tennis racket is formed by adding together two components. The handle, well, obviously, there it is, there's the handle, and what we describe as the head of the racket, which is presumably from there to there. And those two parts can potentially vary independently. They might not, of course. It might be you get a big racket and everything about it is big. But if we assume that both parts are independent of each other, with all its limitations of whether that's true or not, you have a new random variable, which is the length, the overall length of the racket, all the way up, all the way down. And it's made up of two parts, and it's not surprising that the average length of the racket you can basically think of as the average length of the handle plus the average length of this will give us the average length of the racket. Now that seems obvious. What's slightly less obvious is what happens when you get the standard deviation. If you knew the standard deviation of the handle, for instance, and you knew the standard deviation of the racket. Now, to get both of these adding together, you'd need to get this handle as maximum in terms of its variability as big as possible all the time, and this one as big as possible, in order to achieve the standard deviation, the range of values of the rackets as big as possible. And that's probably unlikely to happen. You'll probably get a mixture of some, it might be, because these are meant to be random and independent, so you might find you get some of the heads are a little on the small side, and some of the rackets are, the handles on the bit slightly on the big side, in the random nature of of these things. And so you end up tending to find that the standard deviation of the entire racket is less than the standard deviation of the two parts. Effectively, it kind of comes down. But what is true, what we can say is true, and this is something that's certainly worth us learning, is that even though the standard deviations don't add, the variances do. So I want you to copy that down. The variance of 1 equals the variance, x plus y, sorry, is the variance of x plus the variance of y. This is important. Write it down. And because of that, and our other, this rule here, we can go a bit further, and I want you to copy these down as well. The variance of ax plus by plus c, you'll notice it's a more complicated version of what I just wrote down, is the ae of x, be of y plus the c. But the variance of ax plus by plus c, the c still disappears, doesn't matter, but I square both parts. So that's really just a more complicated version of the variance of x plus y equals the variance of x plus the variance of y. Let's use these in a couple of questions then. So we've got the mean thickness of a burger bun, the base of a burger bun in fact. They tell me about this base, and they say this base has got a mean of 1.4. In fact, I'm going to write the mean on this side and the variance on this side. And the variance, it says, is 0.02. And then we got the burger part, the thin burger part. Well, it's actually thicker, it's 3 centimeters, 3.0, but it's got a variance of 0.14. And then the top part, it says it's got a mean of 2.2 and a variance of 0.2. Okay, find the mean and standard deviation of the height of the whole burger. Well, I suppose the height of the whole burger is the height equals the base plus the middle plus the top. There you go, that's good enough for me. And therefore, using my formula, notice there's no numbers in front of this. It doesn't say like 2b or 3m or anything like that. Assuming that the thickness of each part is independent, yeah, well, I would have wanted that. So that my expectation of my height is simply equal to the 3 parts added together. So it's 2.2 plus 3.0 plus 1.4. That sounds like to me 6.6. Now, what's it want? It wants the standard deviation, but I haven't got a rule for standard deviation, so instead I'm going to have to go for a rule of the variances. The variances of the height will be the variance of each one added together. So that's okay. I can go 0.2 plus 0.14 plus 0.02. What's that equal? 0.36. But that is the variance, therefore I need the standard deviation, and that's the square root of 0.36. Sounds very much to me like 0.6 centimeters. So notice there, even though I wanted the standard deviation, I had to play around with the variance. That's the only rule I know. I don't know a rule for the standard deviation. So I did the variance formula, just added them together and then square rooted. So that sounds quite straightforward. But it was quite straightforward, I suppose, because this formula here was quite straightforward. It just said add them together. 6.6 and 0.6. Good, it worked. Now, just be aware of a couple of things. So if I'm ever given the expectation, or want the expectation of 2 different observations of x, that is the same as basically saying, well, say I was expecting to get one observation, say it was a height again of 30, and the next one I'm expecting to get a height of 30. Well, really, that's the same as getting I'm expecting to get a height of 60, I suppose. That's really all it's saying. It doesn't work with variances though, be careful. The variance of one plus the variance of the other. Notice it's equal to the variance of one plus the variance of the other. So that's 2 variance of x. But if I have a 2 in there instead, notice now it's not just one observation plus another observation. It's the same observation, but I've doubled it. Now on this occasion I can bring the 2 out to the front, and when I do I have to square it. 2 squared is 4, and therefore it's 4 var of x. And therefore what I can conclude here is the variance of x1 plus x2 is not equal to the variance of 2x, whereas the expectation of x1 plus x2 is equal to the expectation of 2x. This works, this doesn't. Make sure you know that. Here's an example. In a shop, the mean mass of an orange, so orange bar, is 84, and the standard deviation for the oranges equals 11. Okay. The mean mass of lemons, lemon bar, is 64, and the standard deviation is 6. Standard deviation of the lemons is 6. The shopkeeper thinks that if 4 lemons are picked at random, well, that sounds to me like L1 plus L2 plus L3 plus L4. 4 lemons. Notice not the same lemon, it's 4 lemons. Their total mass will be more than 3 times. Well, typically you would now take away 3 times, more than 3 times the mass of a randomly selected orange. So 3 lots of O. If D is the difference between the mass of 4, so that's D really. The mass of 4 lemons and 3 times the mass of the orange, find the mean and standard deviation of D. Okay, now I understand. Now, critically, in order to get E of D, I just do, well, it's E of all of these things here, and you can just do 4 times E of 1 lemon minus 3 times the E of an orange. Doesn't matter with expectations, means. So I think it's 4 lots of 84 minus 3 times a 64. Have I got that the wrong way around? Yes, I have. It's 4 times the 64. It's 4 lemons minus 3 times an 84. So what's this mean? 4 times 64 minus 3 times 84. I get 4. Not sure if that's right or wrong, we'll find out in a bit. And that's 4 grams. Now, that's it, what I'd expect to happen. What is the standard deviation? Well, I can't do anything with standard deviation, but I can with variance. So the variance of D, well, critically, let's just go back a step. We have said if we want to get the variance of x1 plus x2, it just equals 2 times that variance. So we've got the variance of these things. This will just simply be 4 times the variance of the lemons. And then we're going to have to deal with the next part. It says the variance of 2x, where you double it, you have to take that number out. Okay, so it says minus. Well, that's for a start. You've got to be careful. It's plus. Plus, because when I take that minus 3 out, it becomes 9 times by the so the variance of the oranges. What was the variance of the oranges? I'll write that down in a bit. So this becomes 4 times the variance of the lemons, which was 6 squared. Obviously that's a standard deviation. Minus, plus 9 times the variance of the oranges, which is 11 squared. So if I just do that calculation, 4 times 6 squared plus 9 times 11 squared, I get 1233. Now, on the face of it, that's completely wrong. But of course, this is the variance. So now the standard deviation is the square root of 1233. Which it says is 35.1. Look at that, it even works. Now, I haven't got time to do the last question, which I've got for you to do, and we'll worry about that next time. But in the lesson, I'll do that. And exercise 8a then will be based around making sure you can do these. Thank you very much.